This is the Amp Hour Podcast, released October 29th, 2024. Episode 681. Compact High-Speed Design with Lukas Henkel. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Lukas Henkel, the CEO at Ovitech.
Hey, Lukas, how are you?
I'm doing great, thanks. How are you?
Yeah, good. Usually I'm found on a random Tuesday like today, marveling at your LinkedIn posts of
Thank you very much.
high-speed designs and simulation and just ridiculous density and I don't know, just all the things that you seem to post about. So
Great.
Keep doing that, please.
Thanks for leaving a follow.
Yeah. So let's talk about that a little bit. I mean, you are the CEO of it's a design shop, right? I mean, you're doing designs for hire. Is that right?
Yeah, exactly. So Ovitech is like a mixture. We are primarily an engineering company here in the heart of Bavaria. But we are also doing our own open source projects. Or we have, I would say, a passion for open source projects. And now we're also making products out of that. So we are currently working on the Raspberry Pi compatible module. We're also working on an open source laptop. We're trying to apply what we learn through our engineering projects into our own open source products.
That's great. Wow. Well, definitely we're going to come back to the Raspberry Pi replacement module. Let's talk a little bit about the things that you find yourself doing. I mean, it seems like if I had to kind of summarize just from memory, and I do have your feed in front of me too, but this is me without looking. People have to trust me. I think I remember just like high-end Linux-capable systems that often interface to things like vision. Obviously, lots of memory, but just the compactness is one of the big things there. Is that a fair kind of summary of the work you often find yourself doing?
Oh, I would say so, yeah. So we're doing quite a bit of embedded devices, especially Linux-capable embedded devices. And we also have a passion for miniaturization. So we're working on a project actually on a little system and package where the goal is to pack as much compute power on a little space as possible.
Yes. Yeah. That's a theme that continues throughout. I mean, I remember also you had one where you were putting just gobs of stuff into like an SD card form factor. Is that right?
It's the same project actually. So this is also also the open source SIP. And one time I was just looking at the form factor and said, wait a minute, this could fit very nicely in a form factor of a small SD card. And so I tinkered with the idea a little bit and designed a small baseboard. And now we have a Linux capable and also wireless SD card. I mean, it's not a new idea. These things have been around for quite some time, but they are quite limited in their compute power. And also you can't run custom code on that. So I thought, why not? If we already have the SIP, why not just put it in the form factor of an SD card?
Yeah, and it is I was going to say the hard thing these days is probably finding a full-size SD card like holder, right?
Yeah. True.
Like everything switched to mini or micro or whatever it is. Yeah, micro is the one that is common.
Absolutely, yeah. It's just mostly camera stuff, I think, that uses full-size SD cards now.
The SD card is a good example, actually. So we have these humongous, form factors, relative, of course, to just for my fat fingers, right? Like I have fat fingers. I need to be able to plug this thing into a computer. At some point, they existed because that was the technology node. But like everything is leapt past that. It's just like thinking about chip scale packaging and just the scale and the scale difference of I don't know, like even the what's actually triggering the cellular part of the modem on these packages that I use that are already miniaturized. Like they're always scaled up and up and up and up to make them usable to board level PCB designers like us. But you're starting to kind of just take it down in the other direction. So I guess my question is, where do you start running into the limitations, right? Like of this miniaturization?
Well, at the moment, it's really just a price limit, I would say.
Price limit?
Yeah. So at the moment, what we're trying to achieve, we have a product in mind where space is at a premium. So we really have to cram very, very much compute power in a small volume, and that's why we've looked into this open source SIP. And at the moment, we are using standard PCB technology. So the design that you can see or that I've shared online as well is just a standard board, standard in quad marks, because it's still high density. So a trace width is 75 micron spacing as well. The vias are also quite small with 200 microns total diameter and 81 or 85 microns drill. So it's a very high tech PCB, but it's not at the substrate or interposer level. That would be the next step, but this step is quite a leap in terms of price. So we tried for the open source SIP, we tried to use a standard PCB manufacturing process just to manage the price of the whole project, but also, since it's open source, to make it possible for other enthusiasts or other companies even to adjust and customize the module for their needs. And it would be a huge hurdle if we used some highly exotic process to manufacture this. This module. So we are still using somewhat standard-ish PCB processes.
Got it. Yeah, so like off the shelf at the very least, I would say, right? The fact that it is still a PCB and it's not like there's no chemical. Well, I guess there's no direct chemical. I guess it is. And then I was just like, that's how they do PCBs as well. They do chemical etching.
True. Yeah.
There's no CVD or
exactly.
Dry etching happening.
Yeah, exactly. It's just in quad marks. I mean, it's still, as I've said, a fairly advanced PCB. So not every PCB fab will be able to manufacture this board, but there are still quite a large number of board houses who can take on this challenge, and you don't have to go to interposer level or a silicon level packaging company to build something like that.
Yeah, right. And that is, I actually just caught up with the folks at Octavo, and they are kind of down at that level, right? They are basically taking silicon and putting it in interposers, but it's like a polysilicon level. I don't actually know what they're stacking stuff up now, and they kind of put stuff side by side, but that's different than what you're talking about, right?
At least at the moment it is. We are also planning to go down the road, actually.
Yeah, everybody needs new challenges, right?
True, exactly. Exactly. So one thing we are also looking at for the open source SIP. So I can walk you through the steps of miniaturization that we have planned.
That's great.
So at the moment we're using conventional PCBs and also conventional components. In the next step, we will be starting to embed components into the board itself. So instead of using conventional inductors, we will be using silicon-based inductors. There is some very interesting, work going on with our cooperation partner. And unfortunately, I can't share too much about that at this point in time. But there will be silicon-based inductors that you can also buy off the shelf. And one neat thing about those is they are only 200 microns thick, so very, very thin. And you can embed them even in small or very thin boards as well. So next step of miniaturization for us will be to move those conventional inductors into the board itself. This will give us some room on the top side of the module for, either just shrinking the module or put more features on the module. And the next step will be then to source the memory and the storage dies as bare dies, bondable bare dies, put it on top of the SoC. So stack everything on top of each other and just bond them to the board substrate. But at this point, we will also have to move up in the technology class and really think about interposer level design rules. So 10, 20 microns space width and tracing. Standard PCB won't cut it in this case.
It's interesting too, because so like what I'm hearing as you are saying these things, it's like all of these things are possible, but it's just completely irrational to do it in low volumes, it feels like. So you also need to be able to find something that's like common use case enough. Like, so you're saying it's a SIP, it's, a general purpose SIP, but you have to get enough volume to actually make that a reality so that it's worth that NRE, worth the time investment to actually make this all happen.
Absolutely. Yeah. That's also one reason why we decided to go with a standard PCB in the first step, because the manufacturing cost for these boards is also quite a bit higher than standard PCBs, but it's still manageable.
Sure. Yeah.
But once we actually move one step up in the miniaturization, in our miniaturization game, I would just say, then of course we're also talking about other volumes that we have to run this module at in order to make it just financially feasible.
Yeah, totally. Yeah, I don't know how do you even judge that? So like, when do you decide to take that next step? Like, is it volume based, or is it just curiosity based, or is it truly? Is there actually anything constraining your space in this case? Like, you're like, oh, this doesn't fit. they need it to fit in blank.
Yeah, there actually is. So the open source SIP is only one part of a project that we are currently planning. So we do have a device in mind where we would like to use the SIP. And at the beginning, we were actually planning to just not do a separate module, but integrate the SoC and the memory on the main board in our target device itself. But we decided that we want to swap out the CPU in the future. We want to support also other CPU platforms, and we also received some requests for a module form factor of the CPU that we are using, because we are using the IMX8 ULP, which is a very painful package to work with. It's a 0.4 millimeter chip scale package, and not everybody is looking forward to routing something like that. And so since there was some interest in the community, we decided to design a SIP. We shown the design online and got a lot of requests from the industry to manufacture and use this thing. So there is definitely some interest out there. That's why we decided to go with the SIP approach and just use it as a drop-in module for our own application. But our application is how much can I share about that? Yeah, for now I just leave it at it's very space constrained.
Okay, yeah, that's fine. Reasons to follow Lukas on LinkedIn to see all the stuff.
It will be open. The final project will be open source as well. So at some point, it's definitely worth checking it out.
Well, and so the SIP is the one where the chip scale package is kind of like embedded underneath, right? That's the one that we're talking about here. It's like routed out and then a big Kingston on top. Is that the one we're talking about here?
Yes,
I'm just
exactly.
Looking at
Exactly.
Yeah, okay. So, and this might, again, people that already follow Lukas, and we'll definitely have links to his LinkedIn so you can follow him. One thing that's interesting about that is showing the Kingston. So I'm going to just try and describe it with words, which I'm sure will fail me, but we'll have links in the show notes, of course. The memory is so basically like top side of this SIP, and this is PCB material you're saying as well.
Yes. Yeah.
Okay. So top side of the SIP, large Kingston RAM, looks like. I don't know how much. Then looks like power switching with some ridiculous density caps and inductors. Is that right? In the lower left, the top side?
One point.
Yeah. Bottom right is sensors or oscillators. I'm not sure what that is actually.
Bottom right, that's just oscillator. So real-time clock and the main oscillator.
Okay. Yeah. And then the bottom side is a footprint. That's the SIP footprint you're talking about. But then routed into that, like, so basically like a sunken living room. If you've had a house in the 70s in the US, basically that's where the processor lives. So that it's basically when the whole SIP is mounted to the board, the IMX8 is upside down, right?
Yes, exactly.
Got it. So now I, as a designer, I could go and take this SIP footprint. You're saying that the Open Visions would potentially swap that out for a non-IMX8 in the future, something different, some different part, or just taking advantage of that. But basically from a drop-in replacement, now I only need to worry about this open source SIP footprint that goes onto my board. Is that right?
Yes, exactly. And the footprint we've tried. I mean, we are all PCB designers here at Open Vision, so also our focus is also to make the lives for PCB designers easy. So we try to choose a footprint that's easy to route. The pin pitch is relatively comfortable to work with. It's 0.8 millimeter, so it's pretty standard BGA pin pitch. So you don't have to use highly expensive stack ups or highly dense PCBs to break out this package.
So I actually just gave a talk on this. Lukas and I was talking about this before the show, but like I just gave a talk to the Zephyr group about the benefits of doing this kind of module abstraction, right? So now this footprint is the same. I created a footprint, which is like is insanely larger than this. Mine is, so this is, I don't know, I don't see the dimensions on this. The one I'm doing is 24 by 34 millimeters. This looks like this is what, like 10 by 12 millimeters? I don't even know. And it's doing way more.
Yeah, it's 14 by 16 millimeters at the moment.
14, oh my gosh, so big. Yeah, and this is a full Linux system, and mine is definitely not. But I really agree with this, because honestly, for me, it's kind of like PTSD from the 22, 23 of just like not being able to get a part, right? So if you have that IMX8, so if I had said, oh, you know what, I don't need this Open Vision thing, I'm going to go and I can do layout, I'm going to put my own IMX8, whatever. The benefit of module always is, if that IMX8 isn't available, or really anything on this module isn't available that would have been on my PCB, I can just potentially get a different SKU of this SIP, and then still be my line can be up. That's always the benefit.
Yeah, absolutely. And that's also another thing to mention. That's one reason why we decided to go open source, actually, because we want to give the complete ownership of a system to the designer who actually integrates a SIP. So what I mean by this, if I buy a SIP, for example, from Raspberry Pi, I'm always relying on Raspberry Pi to provide the complete SOM with with all the parts that I need. And during chip shortage, there also was a shortage of Raspberry Pis. We don't know for which reason. It could be that the Ethernet 5, for example, wasn't available.
And now, if you just need one part to be busted, and then you're lying down. You know?
Exactly. And now, since we're doing this open source, the designer who is using our SIP or our SOM can just take a look at the bill of materials and say, hey, well, we don't need this particular part that's currently holding up the delivery schedule. Just depopulate it and deliver the board to us without the specific component, or they can just adjust it themselves, of course.
Yeah. Totally.
So the ownership, I mean, SOM or SIP is really the central building block for many systems. So in my opinion, the designer who's using the central building block should also have complete ownership over the building block as well, because it's at the heart of the system.
We are completely in sync on this. Yeah. I think the other thing too is that, like, just from a life cycle, right? So I'm designing an industrial product. I want to use this SIP. That's great, and that's what it is today. But then 5 years from now, I want to just start designing with more horsepower, right? Surely, if the SIP footprint stays the same, if we have a flexible system that Linux provides, then we can just target the same pinouts to this SIP footprint, same functionality. Obviously, I have to test it as the board designer, but I then benefit from better technology. Basically,
absolutely. The modular approach is just great. I mean, of course, it also has some downsides. You're always paying for interfaces that you wouldn't necessarily need. But the advantages, as you said, is just immense flexibility. That's also something I very much like about, I'm not sure if you know the framework laptop. So this is the modular laptop concept. And I just love that, because you can just drop in another motherboard once your CPU is outdated. And there's really no other manufacturer who can provide this level of flexibility.
Yeah, and that's also at the truly drop-in level, right? Where it's not soldered down, it's at a connector level, right? That's almost like a repairability and like true ownership type of thing. That has a different flavor to me. That's less of like oh crap, I'm lying down, than it is like I don't want to waste and like there's nothing particularly fancy about my current laptop that I wouldn't benefit from. It's not like I have such a crazy spec on my current laptop that I wouldn't benefit from upgrading it later. So the general compute idea definitely, it benefits us all. That's I think another thing too that you wouldn't think about, but I would think about, right? I'm looking at this SIP, and again, we'll have links in the show notes. This is just something I can't do. I mean, or I can't do efficiently, or it's not worth it for me to do it. If I'm a consultant, it's not worth it for me to do it for my clients, because the time to do that is just not realistic. So that's why, the CM4, the compute module 4 from his Raspberry Pi as well, there's nothing special about the connectors on there, the capabilities, the interface out to the world, but it's that kind of like IP, it's like an IP block that I'm basically dropping in.
Yeah, exactly. It's a proven design. There's a big community around that design as well. So you have quite a lot of reference designs on how to actually use this kind of module. And you're just saving a ton of work and also potential debugging work in case memory training between the SoC and the onboard memory fails. These things are very hard to debug, and if you don't have the tools or not the time, then probably just get a SIP.
Right.
Makes life so much easier.
Yep. Why is the memory so big? What is the limiting factor on the memory here?
So this is actually EMCP module, meaning there is both the memory and the storage integrated in one package. So we have
interesting. Okay.
4 gigabytes of LPDDR4X and 64 gigabytes of eMMC. And it's just memory dice are large. So it's really just the die size. In this package, I would say the molding is like, I don't know, maybe 10 to 20% of the total volume. The rest is just dies stacked on top of dies. And so the only way to further miniaturize this design would be to stack the memory on top of the SoC.
It's basically modules using modules.
Yeah.
Exactly. Like, on that talk I gave, I was a little embarrassed because I'm basically like, I'm putting an RF module under an RF can, right? That's like my idea. It's, I'm midway through. I'm not like actually doing it yet, but like it's embarrassing to be like, I can't do. I'm not gonna do chip down design for a cellular module. Like it doesn't make sense for me. But also I want to like shield the rest of the stuff from any crap that I put on a board. But it's like it's always modules all the way down, right? It's like basically going to get down to the transistor level. Like it's we're always implementing on top of other people's modules. It's just that cost, like you mentioned, of having interfaces, having additional abstraction for each individual level.
Yeah, absolutely. I mean, if you look at chip design, it's the same story there. You get your IO pad library, transistor library from your fab or from whichever provider you are using. You get those pre-manufactured IP blocks that you can drop in your design, and in this kind of scale, there's really no other way to approach it because so much work has gone into developing these building blocks, and if you would really like to do everything from scratch, that would take years. Really not
lifetime. Feasible. Yeah. What about the so again, I mentioned CM4 from Raspberry Pi. One of the benefits there is that they have builds that are standard Debian builds for that sort of thing. So then, do you find that the community has already started targeting this IMX8 with like Yocto or Buildroot style systems, or how is that going to work?
So yeah, we will definitely be relying in part on the community to help us with the BSP. But we also provide our own build on our onboard support package when we actually launch the module, so that people have something that works out of the box. That's definitely necessary.
Tiny little box.
Yeah, tiny little box. But yeah, I mean, one of the unique selling points from Raspberry Pi is just the huge community. So a lot of people are working on implementing drivers for their specific use case as well. Maybe not necessarily drivers, because there you need also some documentation of the SoC, which is not available. But the ecosystem is just so huge, and the community support is so large that there is really a lot of things going on that would be very difficult to do for a small company.
Right.
So we're definitely relying somewhat on the community for the Pi MX8 as well. At the moment, there's not a lot of work going on, but that's just because we haven't officially released the design files yet. So we want to launch the crowd supply campaign first, and after the campaign is successful, we will then provide a GitHub link with the Altium files, and also we will provide a keycard project. So we convert the Altium design to a keycard. So folks who are not using Altium can also work with the design. But once that data is public, we hope to see also a lot of engagement from the community. We get a lot of requests at the moment, and I'm also for people who are interested, sharing those files even now before we've started the crowd supply campaign, because a lot of people just want to get started. They want to maybe even design a baseboard for the Pi MX8 or look into the firmware side of things. And so I expect to see a lot more community interaction once we actually published all the files.
Okay, great. Let's disambiguate a little bit here. So as well, so you have your SIP. So the SIP has the same IMX8 on it, has the memory on top. We'll have photos of that. that is in development. The SIP is not going on the Pi MX8. Is that right?
Yes, that's right. So the SIP, being a very, very small form factor, we have our own product in mind for that also requires this level of integration. The PCB for the Pi MX8 is a little bit more low tech. It's still an HDI design, but it's not as expensive as the SIP, and it also uses another processor. So on the SIP, we have the IMX8 ULP, which is the ultra low power variant of the IMX8 lineup, which is targeted specifically for wearable devices or IoT devices with very low energy consumption, while the IMX8 M Plus that we are using on the Pi MX8 is catered more towards multimedia and compute-hungry use cases.
Tiny security camera versus high-end camera.
For example, yeah.
Yeah. Okay, cool. All right, that's a good one. And so now Pi MX8, you mentioned, is a crowd supply campaign. We'll have links to it. That is launching in the project launch on crowd supply will start weeks to months away.
3 to 4 weeks from now, yeah.
Okay, great. Probably 2 to 3 weeks from when this is posted, and you can sign up now. And then on crowd supply, and then that'll be delivery rough time frame.
It depends. So we have a few requests that we have to fulfill or that we want to fulfill first, also as part of the crowd supply campaign. But general availability will probably be either late December or early January next year.
That's still pretty fast for a crowd supply campaign. That's already you're already well on the way. So basically, you're just kind of gathering numbers and ready to launch that thing.
Yeah, we have done this. This project has been going on for quite some time now. At some point, we started this project not even with the intention in mind of actually selling a Raspberry Pi compatible module. So this project actually started as a part of the open source laptop project. So we wanted to have a CPU module that we could drop into our open source laptop. And in case our CPU module doesn't work, we can still use the Raspberry Pi. That was kind of the thought behind that. But since we've gone public with our idea of using a CM4 module for our laptop, people really thought this was a great idea, not only for the laptop, but also as a standalone module. And we kind of developed this project into a direction of a standalone product.
So that makes sense. Yeah, and then like you said with the framework too, like if you have something that's using that kind of somewhat now standardized CM4 footprint with the high density connectors, you can continue to upgrade your laptop using new modules from yourself or Raspberry Pi or really anyone who adopts that same kind of footprint. And matches.
Exactly. Yeah. Unfortunately, at the moment, some time ago, we had to move away from using the CM4 form factor for the laptop project, just because we can't fit the compute power that we need on this small of a footprint.
Oh, interesting. Okay.
And at the moment, I would be thrilled to actually use the same mainboard form factor as the one used by the framework laptop, so that the modules would be interchangeable. So my idea would be to design an open source mainboard in the same form factor as the framework mainboard. And
to drop the whole thing in then, so it still has this module on it, and basically it's a drop into the framework module.
Exactly. So we could use the mainboards that are also used in the framework laptop, but enthusiasts could also use our open source mainboard in their framework laptop. So there would be a two-way approach. But this is just my idea. Or my ideal conceptualization.
A pipe dream right now, but maybe someday.
Yes, exactly. Yeah. Exactly.
Got it. Okay. I think I've seen enough of your stuff that I wouldn't be surprised if we saw it. How about that?
Thanks. Yeah, it would be great.
Yeah. That's great. Yeah. Okay. So then, let's talk a little bit about the CM4, the Pi MX8. So the CM4 replacement module. Differentiation. What are some of the differentiations that people would expect to see between CM4 versus your design?
Yeah. Well, in terms of features, we pretty much tried to match what the Raspberry Pi has to offer. So we have our own our onboard Wi-Fi chipset, the onboard Ethernet PHY, standard memory, standard eMMC. We have some extra features on there. For example, we have SPI flash that will also contain a backup partition that the user can edit freely, which might be interesting for more mission critical in quote marks applications.
Okay.
What we have on there is also a secure element if you're doing some sensitive stuff. For example, if you're using this kind of module for the design of a cash register, you can use the a secure element coupled with NFC controller to do a safe transaction.
Cool. Okay. Which secure element do you use for that? Is that that's for like holding private keys and stuff like that, or is that a secure element outside for the actual NFC stuff?
Yeah, it's a dedicated part. We're using the SE050 from NXP.
Okay, cool.
So it's interfaced over I2C with the SoC, and the same I2C interface is also broken out on the CM4 connectors. But cool. Other than that, the features are pretty much the same in terms of which kind of interfaces you have available. It's just the different CPU architecture and the open approach that really is the USP for our customers, so that they have complete ownership over the design and can also use for example, advanced features for image processing that come with the IMX8 processor.
But you're no longer targeting the Coral TPU. I thought I saw that on there.
Yeah, so we have a footprint for the Coral TPU on there, and we're also supporting this module still. But we are currently integrating the Halo 8L deep learning accelerator. But at this point, we are not sure if this will be an open source design as well, because there are also some policies around the Halo chipsets. It could be that this is just another version, but either way, both versions will have an HAI accelerator on board. In addition, of course, to the internal HAI accelerator of the IMX8.
Sure. Yeah. The Coral thing I wasn't sure about. Like I had followed some of the Coral stuff over time, and like I know that I only know it because the tensor processing unit, and that's the T in the TPU. But like I thought they were end of lifing that as well. I thought the Coral project was kind of maybe not.
Well, there's still
long term.
Yeah, this is the thing. When we started this project, which was about 3 years ago, things looked a little bit different at the moment. Yeah. Of course, the TPU was around for some time as well, but there were still some new developments going on and a bit more active community engagement for this module as well. And if I were to design the PyMX8 now, I probably wouldn't have chosen the Coral module. So this is a little bit of a historic artifact, but there is still interest in the module.
Benefits of modularity, right? You can have multiple SKUs, and you target different ones, and
exactly.
And then it's up to the firmware people to just make it work. Come on, folks. What's the hard stuff here? It's just software.
Sorry. You make people angry.
Yeah, right. Okay, yeah, it's interesting. And just in general, for this kind of like offloaded edge processing like this is for image streaming type stuff, or just generally like machine learning type stuff on the edge? What is, in the general use case, what is the problem you're trying to solve with something like that?
Well, honestly, it started a bit with industrial and embedded vision use cases, especially since the IMX8 has been used for these kind of applications quite widely in the industry. But since we've published our plans for the PyMX8 module, we have gotten so many requests from places where we didn't think we would ever see an interest in this kind of module. So we have people who would like to use this, which is still somewhat expected for advertising monitors. So how would you call it? Advertising panels that you hang in the front of your stuff like that. Smart signs. Exactly. Yeah. So we've got a lot of requests for those. And then we have a lot of requests for niche products. So these would be IoT projects that will be used for either smart city systems. We also have IoT projects for monitoring. How would you say it? So this is a camera system that will be used on mountain tops, on snowy mountain tops in ski resorts, and this could monitor, for example, how prone to avalanches the region is. So this would be another vision use cases. Another vision use
but it's got to be like battery power or solar power, and then it's got to be super sleepy and only detect the just that one event and then go back to sleep, sort of thing, right?
Exactly. Yeah. So another request also we've received was to put this thing on a rocket. That's also maybe another interesting project coming up. But what I'm saying is, at the moment, we are not targeting a specific industry. We are really just providing the tools, and our customer choose what they want to what they want to use it for.
Just to go back to your business too as well. So like you're designing these things that are open source. Obviously, you can reuse them in your own business. But how much of your business is these kind of bespoke, kind of designed for hire type of applications versus making a product that is going to be purchasable and funded, sort of thing?
So I would say the open source projects or our own products are about 30 to 40% maybe of the company revenue, or let's say company resources is a better term at the moment. And the rest is really consulting and engineering services that we provide. And this is another benefit, or I would say a side effect of these open source projects. It's a great tool for marketing and advertising our services.
Obviously, I talk to a lot of consultants on my consultant forum, which I don't think you're on. You should definitely join. And it's always the same problem of like, how am I going to promote my work? I can't talk about my customer stuff. And it's like,
exactly.
It's tough, right? I mean, and then often the full utilization, especially for smaller consulting shops or individuals, that's just like you want to be at full utilization, 80, 90%. So then in that last 10%, usually people are billing for their time or doing learning, whatever. It is a really good doing 30 to 40% of stuff that you can talk about and also utilize in your own work is a great, I think that is a good target, if you can do it. So that's awesome.
Yeah, that was our idea. But if you're already doing marketing, we also want to be able to make some money out of that outside of just the marketing advantages. And that's why we decided to go with the open source approach. There we can generate some revenue by selling the modules, but also have the nice side effect of just going out and showing what we're capable of.
And you can make all those LinkedIn advertising bucks, right? I'm sure that do they not pay you for all those posts you do? They should. I look at them enough.
Nice. Yeah, well, we do have also some marketing corporations going on.
Good.
There's also an article series on the Altium resource pages for the Pimax 8 where you can take a look at how we approach the design of this module. So doing doing a bit of public work or just work in the public domain really helps a small company to grow.
Altium is smart, and it seems like they are in this way. I would be promoting the hell out of your work because the stuff that you're doing with these tools is really, really, really impressive.
Thanks.
Historically, I found out before we started recording, well, I knew that you were part of PCB Arts, but you used to be in charge of the Twitter profile.
Yeah.
When I think I first started learning of PCB Arts. That's I think I was first drawn to your work when you were in charge of the Twitter for PCB Arts as well.
That's okay. So the marketing approach does work out. That's great.
It does. It worked. It grabbed my eyeballs. That's how I met Saber, who we've had on the show as well. That's your co-founder there. And I think I think that seeing high density layout is pretty much always going to work for me. So if I'm your target market, it is working. It is working, Lukas.
Nice. Perfect. I mean, most of the time it's engineers who decide who to hire for external consultancy work or engineering projects. Right. So that's always the thing. If I'm looking at sometimes I'm also looking for freelancers. If we have too much projects going on, we still have to outsource some of our work as well. And when I'm looking for freelancers, I'm just looking for GitHub projects. I'm just looking for some reports on the social media channels to see what they're working on, because I would like to really just see a few examples of what they are capable of. And I found that not enough people are actually promoting their work by just showing what they are capable of. And I understand it. I mean, most of the things are under NDA. But yeah, it would be great to see a bit more open source work from those guys as well. And I think it would very, very much benefit them as well in terms of acquiring new customers.
Yeah, I agree. Yeah. Other things that you showcase on your site as well is the same thing that we had that drew me to Katarina's posts with RF stuff. It was basically like these, animated simulations and things like that also. So Katarina does that with RF stuff.
Yeah.
You do that with signal integrity stuff and simulations and things like that. I mean, one thing that I was surprised with Katarina was that she said she doesn't usually use kind of that animation kind of style in an everyday context.
Yeah.
It's more of a thing that looks good in, helping to highlight and educate, but like less so on an everyday basis.
Yes.
Is it the same for you, or is it more practical to have signal integrity kind of animations?
It depends. I would say if you already know what you're doing, then there's really no benefit in visualizing that, because visualizing these kind of simulations is also quite time consuming. But what I found, especially when I started out with these kind of modeling approaches and just digging deeper into the actual underlying physical processes, it really helps you to understand what's going on and to get a feel for some of the problems you're dealing with. And you have to do some kind of visualizations in order to develop this feel for the problem. But once you have established this feeling, then you sometimes don't even need to run the simulation, because you can take a look at the layout and say, well, I know where the problem will be, or I know there will be a problem, and now you can basically jump over the first iteration loop and just start with a better approach from the get-go, and maybe put a simulation on top of that to further optimize it. But you don't have to run those fancy animations or visualizations every time, because for me it's just really a tool of getting a feel for the underlying physical processes.
Building that intuition and kind of like the skill set. Yeah. You're showing it. You have one post that we'll link in with FreeCAD and OpenEMS. Is that right? Yeah, that's impressive. I've used FreeCAD. Sworn at KiCad or FreeCAD rather many times. What about OpenEMS? I mean, like that as a open source tooling is sufficient for your kind of regular needs, or more of a demonstration in this case?
So OpenEMS is a great tool, and it's really sufficient for most of the stuff we are doing. But this is a problem that many open source tools have in common. For some time now, it really was difficult to use and really a hassle to set up. That's also why I'm promoting this KiCad plugin, and sorry, not KiCad plugin, but FreeCAD plugin, because it just streamlines the process very much and makes it much more accessible to people who aren't coders, I would say, because, for example, with OpenEMS, you have to write either MATLAB code or interface it with a Python command line. And for the everyday hardware engineer who just would like to know what the insertion loss for their trace is.
Right.
That's not really...
just tell me how to do it better is really what I want the software to tell me. It's just be like, please fix my mistakes. Just tell me where I need to, like have a focus, and just like I just need like a DRC effectively for signal integrity to just be like, yes, you did this wrong, Chris. This is a bad idea.
Exactly. And that's the problem with many open source simulation tools. They are written mostly by scientists, and so the focus isn't really on user experience or usability, or just being able to efficiently integrate the tool in your everyday use, in your day-to-day workflow. And but in this case, this really is an option with the FreeCAD plugin. And if you just want to simulate your antenna design or want to run some crosstalk simulations, this is certainly possible with OpenEMS. It's still a bit difficult in terms of the meshing, so you still have to dig a bit into the background of the finite difference time domain simulation topic, especially with the meshing that's used by OpenEMS. But once you've done that, then it's certainly a very usable and capable tool.
Well, once so we had Sean Himmel on the show talking. He's doing FreeCAD classes. I'll tell him to start doing some classes on that too, some scripting on top, and
nice.
Boom, help the world.
Perfect.
What about you have some heat simulations as well with Blender? So that's another one where I've seen Summer, I think his name is, on LinkedIn. He does a bunch of amazing Blender simulations.
Oh yeah.
This is a heat-based one. Is there specialization around doing heat map? It's not even heat mapping. It's like heat flow, right? It's like airflow. It's like CFD. What is that?
Depends on what specific post you're referring to, but we've done both. So static heat transfer simulation, for example, if you I don't know, have an LDO on your PCB, for example, you can run a static heat transfer simulation to see how the heat dissipates in your PCB, or just spreads in your PCB and then dissipates to the environment. See how the neighboring components heat up, and of course just calculate how hot the LDO will get in the end. So this is something that you can do with Elmer, for example, which is also an open source simulation tool. But you also can couple this with a CFD solver. So now you're modeling not only the heat transfer in the solid domain, but you're also bridging the gap by transporting the heat in the fluid domain, and see how natural convection, for example, transports away the thermal energy from a heat sink, from a PCB or whatever. And all of this kind of stuff you can then visualize in Blender. So none of those simulations are done in Blender. It's only the post-processing.
Got it. So you basically have like maps of like basically gradients that are calculated through time or something like that, and then that's what gets put into Blender?
Yeah. So there is...
this is BVTK nodes you said in this post. I just linked it in our StreamYard thing too.
Exactly. So
this is the one I'm talking about.
This BVTK nodes plugin can actually read the solver output directly. So there is an output format called .vtk, which stands for the Visual Toolkit. And this is a file format that many simulation tools use. So in the file, you have a representation of the geometry, or better to say the simulation mesh, which represents the geometry. And with every node in the simulation mesh, you have associated scalar fields, vector fields, tensor fields, and all those fields can be extracted using BVTK nodes, and you can map colors on those fields, or you can assign graphs to see where the vector field is pointing and stuff like that. All this is becoming possible through BVTK nodes by directly reading the solver output. So this is a really great tool for these kind of scientific visualizations.
And the VTK files, the thing that's actually solving that was built into Altium in your case, or that was another third party like Python script type of thing?
So you mean the solver that creates the VTK files?
That's right. Yeah, exactly.
Yes. So these are tools like OpenEMS, for example. So OpenEMS can also export these VTK files. Elmer, which I'm using for static heat transfer and elasticity analysis and stuff like that, can also export VTK.
Sorry, what was the name of that again? Elmer?
Elmer, Elmer FEM it's called.
Okay.
So this is a multiphysics platform which can solve things like static heat transfer, static current conduction. What else do we have? Well, there's quite a lot of solver modules in this package. Linear elasticity, non-linear elasticity. What else we have in there? It's really a plethora of
that sounds
solvers.
like a super program. Yeah.
It is great. Yeah, it also has the bit of user experience problem that OpenEMS had some time ago.
Yeah.
There is an Elmer GUI, but not all features are supported in the GUI. So if you really want to dig deep and use all the features of Elmer, you still have to use the command line interface. But it's.
I think Elmer, which is at elmerfem.org. I think probably the most telling thing is when you go to their forums and it's a PHBB, like the classic PHBB, like just stock He's like, okay, I know what I'm getting into here.
Yeah, exactly.
Yeah,
I mean, the tool is great and very powerful,
totally.
but I mean, it's written by researchers, primarily for researchers. So
function over form, which is really how it should go. Yeah.
Yeah, exactly.
That's super cool. Okay, so now I don't know. This is just going to sound like an idiot. How do you know how to do this? like it seems like some of this is just the constraints over time too, like the complexity of the designs you've been explaining and you showcase, but like I've never needed any of this. Like I probably have needed it, but I just don't know how to do any of it, you know? I don't.
I mean, it's I don't really
Lukas,
know.
Are you a smart person? Is this what the problem is? Am I talking to a smart person
right
now?
No.
Another smart person on the AFR. I swear to God, I keep finding you folks. Yeah,
you're just talking to average Joe, but I have a
sure, yeah.
I'm just very interested in these kind of topics.
Yeah,
it's
the
just
curiosity. That's what gets you. You know.
Yeah, exactly. I mean, it's if someone really has a passion for their hobby, they're always going to be, I don't know, one of the top performers in their field, just because they're spending most of their free time with the specific subject. And
yeah,
I mean, for me, it's a similar story. This is really my hobby, and I'm spending most of my time with this kind of stuff. So I just accumulate knowledge over time, and there is not really a secret approach to this. At least I'm not aware of one, unfortunately. It's just
so I have some theories here. I've been forming this since first meeting Mr. Ben Krasnow. I think folks like him and you and other CN Lore and other very driven, smart people who just stick with it, right? I mean, like there's a lot of stick with it, going through PHPB forums, learning how to script all this stuff, whatever, right?
That's true. Yeah, there's.
What is it? I think some of it is got to be reward structure in your brain. Because like when I come up against some problem like this, I'm like, I'll come back later. But it seems like you and others like you stick with it. So I meet a lot of smart folks like you that like the stick with it is the important thing.
Yep.
So what is that? This is going to get like metaphysical now. What is that reward structure for you like? So like when you solve something like this, when you figure something out, like do you get like a high from it?
Honestly, it's quite the opposite.
Interesting.
For me, it's pretty annoying. So I'm wired in such a way that once I encounter a problem, I can't really let go, even if I would like to.
That sounds familiar. Yep. Okay, sure.
And also, if there's more important stuff that I should tend to, if there is still an unsolved problem, I can't really let it go. So it's it's not really a question of I want to do it. Well, at the start, of course, it is because it's interesting.
Yeah.
But once I dig deep and hit some hurdles, there's just no going back. I have to sort it out. Otherwise, I won't be able to sleep. Quite literally.
Got it. What's the annoying part then? The annoying part is the drive to like figure it out.
No, the annoying part is just knowing that there are some other things that I have to take care of, or knowing that what I'm doing right now is probably not the most important thing. But I just have to do it.
You just can't stop. Yeah,
I just can't
it's
stop.
like an addiction to the problem. Yeah, I know that feeling a little bit. Okay, that makes me feel a little better about myself. It's interesting. Okay, that's good. I'm going to keep developing this theory over time.
Maybe.
Ulterior motive here, of course, as well is like, how do I teach my kids to be driven in these interesting ways as well? Like, I don't know if you could teach it. I don't know if you should teach it, but there's very interesting output. That's what I'm seeing.
Yeah. I think
you're solving cool problems. So that's good.
For me, actually, how I got into this whole electronics field was, I don't know how old I was, probably 9 or 10 years, and my father brought home a broken laser printer. We tore it down and found a little high voltage power supply in there. And the first time I've seen high voltage arcs, I was really fixed because it just, to me as a kid, it seemed kind of magical that it could produce lightning in your home. And that's how I started with the whole electronics side of things. I then started to design my own flyback converters, Tesla coils.
Wow. Yeah,
that's how it started. But I think it was just the exposure to what's possible and to what's out there, and just I just was fascinated by this specific topic, but could have been anything else as well. It's just having the opportunity to find out what really suits you, I think at an early age is very important.
If I tell my kids anything, it's to be curious. That's all I care about, honestly. Just
agree.
Be curious about anything. Like that's the more important thing. Yeah.
Totally
very
agree.
Good stuff. Yeah. Okay, so man, I got a little off track there, but there's a lot of other cool stuff here. I'm not sure we're kind of running out of time, but another question I wanted to ask generally is, so like you and your team are doing some really, really super high density stuff. And so what are things that you've learned in working with this high density creation of boards that are super high density that like are kind of gotchas that, people could start thinking about as they start to dip more toes into the high density stuff? And of course, I'm asking from my own perspective. So teach me, Lukas.
Honestly, I would say if you're already into PCB design, it's a relief if you can move up a technology class, because you have so much more freedom in the PCB design process. But you also have to kind of rewire your brain into more 2.5D or 3D thinking, because if you're just using standard through vias, for example, you have the stack up of many layers and just connect to every layer once you place a via. That's all fine and good and pretty easy to wrap your head around. But when you're doing HDI design and trying to find out how you can optimize space in a specific area of the board, you have to start thinking more about a 3D structure within the PCB, because you're actually routing, of course, over separate layers. You're not just dropping a via down the whole stack. You can move within the stack. You can now even start embedding components into the PCB. And for me personally, it really helped that I also have a little bit of background in CHD design, 3D design.
CHD stands for what?
Just like mechanical design with FreeCAD, for example.
Got it. Okay.
Having this background in 3D design really helped me to get into this kind of HDI design, because my brain was already wired in this kind of 3D space or 3D visualization way.
Yeah, does Altium have when you visualize a 3D when you visualize like the 3D output, just component models and 3D models of those things, is it possible to like look at the stack up in 3D as well? Like, can you zoom in and like kind of hyperscale the stack up so you see that visualization as well?
Yeah, definitely. In Altium, at least in Altium, there's a feature to do that, and I've also used that extensively once I started with the HDI design. And it's the same with the simulation. Once you've developed a kind of intuition for this 3D visualization you don't need that functionality as often as in the beginning. I'm not sure if KiCad, for example, also provide these or a similar feature, but it definitely helps in getting started with HDI design.
There is like a stack up. You can see the stacks if you zoom in the 3D viewer in KiCad, but I'm not sure about. I'm not usually designing with HDI, so like blind and buried vias and stuff like that are just not usually on my plate. And so I'm not sure how that gets visualized. That's a good example, a good question. I think I did that for a board I did like a couple years ago, but it's been a while since I've needed to do that density because most of the time I'm using modules. So
Yeah, but that's definitely very helpful. So if you have a way of visualizing the 3D the 3D stack up, this definitely helps. And I'm not sure, maybe if there is not a built-in feature in KiCad, maybe it's possible to export the copper geometry and just take a look at the layout in a third-party tool. But other than that, I would say it's just trial and error.
Totally.
Just practice, basically.
Yeah, DRC is our friend. It is our teacher.
Yeah, exactly. Yeah, absolutely.
Yeah. What are the normal kind of layer ranges that you find yourself doing as well?
So we are not doing 2 layers or doubles.
Sure. Yeah.
We're moving to 4 layers because most of the time it's just the more sensible solution. Well, not in all cases, but we are not like designing switch mode power supplies for TVs where you have a single layer board and just jumper wires on the second side. So we're usually starting with 4 layer stack ups, and the most layers we have done, I think it was an 18-layer stack up. But most of the time we're hovering around, I would say, 6 to 10 layer board stack ups.
Okay. Yeah, and like you said, I mean, like the costs have dropped precipitously. It's really wild how much cheaper they are than they used to be.
Absolutely, yeah. Also for the SIP, for example. So this is a 10-layer PCB, but it's an any layer design. So there is a blind via or laser wire between each layer. So you can freely drop a wire from any layer to whatever layer you like. That's also where the name is coming from, which gives you a lot of routing flexibility, of course.
Yeah, totally.
And this is quite a complex PCB to manufacture because now you have to now you have a lamination, a plating, and drilling a cycle between each layer that you're building up during the PCB manufacturing. So the manufacturing cycle becomes really complex. And yet still for the SIP, if we are ordering 120 boards, which is not much considering the size of the SIP, so we can comfortably fit that on a A4 size sheet of paper. And having 120 of those PCBs, each board costs us around $10. And at the moment, at the beginning, wild. I was expecting a much higher price tag.
Yeah.
But that's
$50 to $100. Yeah, totally.
Yeah, but that's definitely doable also for the more advanced hobbyists, I would say.
Yeah, that's great. I mean, and so in that case, in the any layer, that is you said that is a laser for each via, or is that
exactly?
Okay. So then they backplate it so that like the ones that aren't going through, like they cap it so that it doesn't go through for certain layers, or they just leave it open.
So there is a laser via, or laser vias only connect, at least in most cases, this is a slight limitation on aspect ratio, but in most cases, laser vias only connect between two layers. So a laser via won't connect all the layers in the stack up. It will only be between two layers. And with the any layer stack up, the laser vias are stacked on top of each other in case you want to connect a trace on the top layer to a trace on the bottom layer. But there is not a single laser or drilling process that goes through the whole board. It's a board stack up.
Got it.
It's just individual drilling cycles for each layer pair.
Got it. So if it's like an 8-layer board and I'm going to go from, so like one through is like from layer 2 to layer 8, but then the via next to it's going layer 2 to layer 4.
Yes.
The 2 to 8 would have laser vias all the way through layers 2 and 8, but they would be plated individually and then kind of like connected in the lamination process? Or
yes, exactly. Exactly, yeah.
Okay.
So there's also different ways on how to approach that. You could either stack laser wires or stagger laser wires, meaning that you can't this depends on the capabilities of the manufacturer. Some manufacturers don't like stacking laser vias on top of each other because it can decrease the yield during PCB manufacturing. But yeah, essentially, you have to connect the vias together during the plating cycle in the manufacturing process.
Yeah.
And now for an 8-layer board, for example, if you're using any layer stack up, now you have, let me think, 5 plating cycles, which just makes the board manufacturing expensive because you have to drill and plate the core
more dips, more electroplating, all that stuff.
Yeah, exactly.
Any board houses that you recommend for this these crazy processes? You don't need to promote if you don't want to, of course.
No,
but
it's all right. Yeah.
Any that you really have had good experiences with?
We are working with Word Electronic for these kind of any layer stack ups, and anything that is more high tech and high density, I would definitely recommend checking them out.
Got it. And that because they also make their own modules, so I'm sure they're lending you some of their processes, huh?
Yeah, they definitely know what you're doing, what they're doing, and they can also help in figuring out what the right layer stack for your application might be. As you said, they have a lot of experience with this kind of stuff, also from their own products. So they are a really good resource. Also, if you are not fully decided on which technology to use.
I didn't even actually know that they is that like a commercial offering that they have, or is it like you had to go get to know your people and
it's just talking to people there. They're not advertising this kind of support online. At least I don't think so.
They are now.
But I've worked with Word for quite some time, and I know what they are capable of, and I know that they are really eager to support these kind of projects. So can highly recommend.
Yeah, I mean, they should promote that capability. That's super cool. I mean, that's good job. Good job, Worth. All right. I think we are running out of time here. Is there anything else with regard to the upcoming crowd supply campaign or other things? We didn't talk about the laptop. Oh man, are there links for the laptop? Where can people find information about your open source laptop?
So at the moment we have an article series going on also on the Altium designer page.
Okay.
Where we just show some insights into the design process. At the moment, these articles are not getting updated, but we have some very interesting stuff lined up for the new updates. So at the moment, we are working on the trackpad design, for example. The keyboard is finished. The next step now will be to sort out the dilemma with the main CPU to see which CPU vendor is actually willing to open source some part of their documentation so that we can use their CPU in our open source laptop.
Got it.
But once that is sorted out, we will also publish articles probably on the Altium resource page for that.
Cool. All right. Well, keep your eyes glued to the Altium blog, and we'll have some links down below, of course, as well. Lukas, thank you for being here, first off.
Thank you very much for having me.
Yeah, my pleasure. And please continue to push out these great updates. You're doing great marketing without even trying for all your capabilities, and we all benefit from learning alongside you. So I appreciate that a lot.
Thank you very much. We'll definitely keep doing that.
All right, we'll see you soon.
All right, thank you. Bye-bye.